Good afternoon, everybody. You're most welcome to this year's Nobel event. I see a lot of young people, but the not so young ones may remember Ögrim and Ormestad, who used to be popularizers of physics on TV, and they were from our department. And when I was a student, I once saw a talk by them, and they said this: when you do something the first time, it's a new thing. When you do it the second time, it's a tradition. When you do it the third time, it's been like this for long as anyone can remember. And that's exactly the point we've reached today, because it's the third year in a row that Mats Larsson is here to talk about the Nobel Prize. And for those who don't know, he is presently the chairman of the Nobel Committee in Physics. He gave the presentation at the press conference, so he really, of all the committee members, probably has the deepest insight in the prize. So that's the first part of today's event. And immediately afterwards, because it's in a hurry, Professor Per Lilje from the Department of Theoretical Astrophysics will jump on stage and add on to the topic a little bit. So I think we just go ahead.
Okay, thank you. Is the microphone? Yeah, I think it's on. I have to, a disclaimer here, I'm not really an expert on cosmology, so I need to say that. And I also discovered a poster over there where you have combined exoplanet and cosmology. So this means that you Norwegian, you had already anticipated this year's prize long time ago, and I have to figure out how this was done. I mean, that I'm very impressed. So, this year's Nobel Prize in Physics has, shall we say, a headline for contributions to our understanding of the evolution of the universe and Earth's place in the cosmos. And I will now describe the first part of the prize, which goes to James Peebles for theoretical discoveries in physical cosmology. And I'd like to make one point here to begin with. When reading about the prize after it had been announced, I saw several comments that they found it strange how one could combine cosmology and exoplanets. But this is a misconception. There is, when you have a divided prize with two different citations, there is absolutely no requirement that there should be any link between these two parts of a prize. The only requirement is that each part should be standing on itself as a Nobel Prize. That's the only requirement. So in this case, we have a connection. I mean, it concerns the evolution of the universe and where we are in this universe. So let's start with James Peebles. And before I go to his contribution, let me remind you about previous cosmology prizes. The first one went to Penzias and Wilson for the discovery of the cosmic microwave background. That was in 1978. Then in 2006, Mather and Smoot received the prize for their observation of the cosmic microwave background, and in particular for they could see that it had a black body form, and that there were also anisotropies in the cosmic microwave background. So that was in 2006. And then finally, the third prize in cosmology went to Perlmutter, Schmidt, and Ries for their discovery of the accelerating expansion of the universe. But all these three prizes have been entirely observational. So this year's prize to James Peebles is actually the very first prize awarded for contribution in theoretical cosmology. And in 1965, that was really the breakthrough. That was when Penzias and Wilson, they measured an excess antenna temperature. They didn't know. They tried to track down what this excess was, but they didn't understand what it was. And by contacts with the group at Princeton, with Dicke, Peebles, Roland, Wilkinson, they understood that this was what they really had observed for the first time, was the cosmic microwave background. And so there were two papers submitted at the same time in May 1965, one from Penzias and Wilson and the other one from the Princeton group. And even before these papers were submitted, James Peebles had already started to think about the cosmic microwave background. And he realized that a critical factor in the formation of galaxies may be the presence of the black body radiation content of the universe. So this was remarkable that he was so early in the understanding of the importance of the cosmic microwave background. And he was also thinking about the Big Bang nucleosynthesis. I mean, how the elements are formed. And in this paper from 1966, he did the calculations of the abundance of helium-3 and helium-4 and deuterium. And then he went through the different nuclear reactions in the early universe. And finally, he came to the conclusion that with the assumption of the simple cosmological model, we have concluded that the primordial helium abundance should be in the range 26 to 28% by mass. And this prediction was now, this is now data from the Planck satellite where they have measured this helium abundance with 0.2% accuracy. And you can see that the number is very close to what Peebles predicted already in 1966. So that was really a remarkable prediction. This you have probably seen this many times. This is the, sometimes you can even see it in Swedish newspapers. This is really the precision cosmology from the cosmic microwave background. And you see here this illustrates these anisotropies in the temperature. And this can then be converted into this, this diagram with the 3 peaks, 3 or 4, 5 peaks, the so-called acoustic peaks, and where these different peaks can be interpreted in different ways. This is basically spherical harmonics on this axis, and the power spectrum on this axis. And so you see here the L quantum number. And these acoustic peaks were, shall we say, predicted in 2 important seminal theory papers that arrived almost at the same time, and they were done independently. One was in Soviet Union. It was Rashid Sonayev and Jakub Zeldovich, and the other one by Peebles and Yu. And here I think one could make the remark that if Peebles has been recognized as one of the, shall we say, giants in theoretical cosmology, he had an equal in Zeldovich, but Zeldovich passed away more than 30 years ago, so by the and it's not possible to posthumous award a Nobel Prize. And quite remarkably also was that Peebles and Yu already in this paper from 1970 they made calculation. They predicted that the power spectrum could have a shape like this. And it's not that different from what has now been observed in the different satellite missions. And the position of the first peak says something about whether the universe is flat. And the position here of this first peak indicates that the universe is more or less flat. The second peak has to do with the amount of baryons in the universe. And the third peak is determined by the amount of dark matter. So this is how one can interpret these 3 peaks. And by then taking the fact that we have a flat universe, the baryons about 0.05, and dark matter 0.26 gives the dark energy density as 0.69. And this is almost exactly what you have also on this poster in terms of the division between baryons, dark matter, dark energy. And this is also sometimes called the lambda CDM model, cold dark matter, and I'm coming back to this in a few minutes. But here you see this division, 26, 69, and ordinary matter. So the dark matter, it has been possible to trace the mentioning of dark matter all the way to 1930 by to a Swedish astronomer, Knut Lundmark, that you see here, who apparently used the term dunkle materia when he wrote in German at that time. Another one who was very early with predictions of dark matter was Zwicky in 1933, and here you see him at Caltech. But what can it be? Of course, this is one of the major questions in today's particle astrophysics and cosmology. We don't know what it is. But in 1982 comes, shall we say, the third important paper by Peebles. In this case also as a single author. And he introduces now cold dark matter, non-relativistic massive particles beyond standard model of particle physics. And he concluded then that the universe is dominated by very massive, weakly interacting particles. That there should also be fluctuations in the background temperature, but that these fluctuations are also well below present observational limits. This was in 1982, remind you. So there had actually been a prediction of fluctuations already in 1967 by Sachs and Wolfe, but they got the level wrong. I mean, they thought that in their estimate they estimated that the fluctuation should be on the 1% level, which is much too much, and turned out not to be correct. But so by the beginning of the 1980s, this was way more than the observational upper limits. So coming back then to the prediction by Peebles, I mean, he predicted that the temperature fluctuation should be of the order of 5 × 10⁻⁶. And the first satellite mission to detect these fluctuations was the Kobe satellite. There had been some ground-based observation earlier, but this was really the first really more accurate measurement of these fluctuations. And this is what Mater and Smoth was awarded the Nobel Prize for in 2006. And here you see this map of the temperature fluctuations. So dark matter searches, that's, as I said, highest priority now in particle astrophysics experiments. And there are a number of experiments going on. There are, for example, this underground experiment with using a large amount of xenon. But from what we understand now, the xenon 1 ton experiment didn't detect any dark matter and could just put limits. But there are a number of other experiments. One was hoping for direct production at the Large Hadron Collider, but that has failed to materialize. There are other dark matter candidates, axions, for example, which seems to be very popular these days. I know that Frank Wilczek, the Nobel laureate in theoretical physics in 2004, who spends time in Stockholm, he is very interested and of course has made contributions to this axion concept. Dark energy. Once again, we have an early prediction by Peebles. He reintroduced the cosmological constant inspired by this inflation concept that had been introduced in the early 1980s. So he, and as you may remember, the cosmological constant lambda was first introduced by Einstein, but he didn't really like it, so it sort of dropped out of fashion. But then it came back in this paper in 1984. That leaves us with two free parameters, Hubble's constant and the density parameter omega, or equivalently the cosmological constant lambda. And one can say that this vacuum-driven universe was really discovered in 1998 in the supernova, when the two different supernova groups started to measure and using the supernovae as shall we say, a standard lamp to estimate the distances, and this was what gave the Nobel Prize then in 2011. Lambda maybe not a constant. Well, this was discussed by Peebles and Ratra in 1988, and one can say this was 10 years before the discovery of the current acceleration of the universe, expansion of the universe. So, rounding off the cosmological part of this talk, I mean, of course, this is a very active field of research. It's not only the dark matter, which is now the biggest question in cosmology, and there are a number of future efforts to try to study the dark matter, and these are just 3 examples of future missions, 2 satellite mission and 1 ground-based. And one can say that this is the book, the standard reference in physical cosmology written by Peebles. And so our picture of the universe is based on physical cosmology, and Jim Peebles' contributions to the theoretical foundation of the standard model have been essential. As I mentioned in the beginning, I mean, the observational cosmology has been well rewarded with Nobel Prizes, but until now it has not been possible to award theoretical contributions, and they have, of course, been extremely important. I mean, how to interpret all these observations. And Peebles, as I showed you, he was already from the very beginning, even before the first publication of the cosmic microwave background, he was making predictions of the importance of this radiation. So now I come to the second part, which is the discovery of an exoplanet orbiting a solar-type star. The solar-type star is 51 Pegasi, and this is Michel Mayor and Didier Queloz. You see, here is Mayor and Queloz. Queloz was at the time when they made the discovery, he was a PhD student with Mayor. And here, this is now an October evening in Stockholm under ideal conditions, of course. You see the different star constellations. And in the star constellation Pegasus, we have 51 Pegasi. I would say that in Stockholm, we couldn't see it by naked eye. I mean, you would have to go out in the countryside where it's dark in order to see it. It's about 50 light years from the Earth. And I just want to say a few words about how really the physics behind how it's possible to detect exoplanets. If in a star, you have a hot, dense interior generating radiation, which is then transported out and then goes through the photosphere. And the photosphere contains atoms, and if the star is sufficiently cold, it can also contain molecules. And in this radiative transfer through the photosphere, there will be absorption by these atoms and possibly molecules. And this absorption gives rise to dark lines in the spectrum, like this. If you go from red to violet, you see few of these dark lines. And this is really the essential for the observations. If these dark lines wouldn't be here, it wouldn't be possible to use the method that is now used for detecting exoplanets. Here you only see a few absorption lines, but in practice, if we have a star here and disperse the light from this star, there are essentially thousands of absorption lines. And in the observation of the Mayor and Queloz, I think they used about 5,000 lines. And the observation is based on what's called the radial velocity method, because usually it's not possible to observe exoplanets directly because they are just too weak. I mean, They don't emit light by themselves, just the reflected light from the star. And this is too weak to be observed directly. So one relies on the radial velocity method. So if you imagine that you have a star here and a planet orbiting this star, of course, what happens is that they both will orbit through the center of gravity of the combined system. It's a little bit exaggerated here. Usually the center of gravity would be within the star, but for illustration, I think this gives a clearer picture. So here is the star rotating like this, and the planet is rotating like this. And when the star is on its way away from the Earth, there will be a redshift in the radiation. And when the star is moving towards the Earth, there's going to be a blue shift. There's of course the Doppler effect in language of physics. And if you're not a physicist, you have heard the acoustic Doppler effect, I'm sure, because when you have an emergency vehicle like a police car or ambulance or something, and you're standing on the sidewalk, and when the car is moving towards you, you hear a high-pitched sound, and then immediately when it has passed, this pitch will lower it quite drastically, so we can easily observe it with our ears. I would assume that if you have experienced the optical Doppler effect, that would probably have resulted in a police car stopping you and saying that you have been speeding. They use a laser radar. And of course, the radial velocity method had been known since long, and it was developed during the 1950s and 60s to study binary stellar formations. The instruments at that time had not sufficient accuracy to discover exoplanets. And just to give you a number, I mean, the sun's radial velocity signal induced by Jupiter, oops, I see it's a misprint here, is 12 meters per second. So just a little bit faster than the fastest man on Earth can run. And in the 1980s, one can say that the pioneering group in the search for exoplanet was Bruce Campbell and he was a postdoc at UBC Canada, and Gordon Walker, who was the professor, and they initiated observations of stars with a spectrograph that could measure radial velocities down to 15 meters per second. And they were using the Canada-France-Hawaii telescope on Hawaii, on Mauna Kea, which is really, Mauna Kea is really an ideal location for observatories. And their strategy was to have a spectrograph that could disperse the light from the star. And in front of the spectrograph, they added an absorption cell with hydrogen fluoride gas. And the idea was here to have a reference spectrum generated from this hydrogen fluoride gas and overlapping this spectrum from here on the starlight with all these different absorption lines. So, and of course, since the absorption cell is fixed in front of the spectrograph, all these absorption lines will remain fixed. And then they try to see how these black absorption lines from the star was moving back and forth because of this motion of the star. Of course, there was an advantage to have an absorption cell in front of the spectrograph. A disadvantage was that, and it's clear from the name, I mean, the cell will absorb light. So you have to use rather strong stars in order to see something. And they initiated a campaign which included 21 stars. They went on for more than 10 years and came up with negative results. They wrote a review article that was published in August 1995, and including results from other groups that had started at that time. And their conclusion was that there are no observed exoplanets. So this was work that started in the early 1980s and went on into the 1990s. And another group that has started in the 1990s was Geoffrey Marcy and Paul Butler. And they used the Lick Observatory in California. And they used the same idea as Campbell and Walker. It's just that they used molecular iodine instead of hydrogen fluoride. Hydrogen fluoride is a rather corrosive and aggressive gas. Molecular iodine is a little bit nicer to work with. And according to the August 1995 review, 25 stars had been observed by Marcy and Butler, but they have found nothing that far. Another development took place in Switzerland, and this was Major, who in 1994 completed a spectrograph named LOD. And Major had extensive experience from studying binary systems. So he understood very well the stellar physics, and he also understood very well how to design a spectrograph that would do the work better than other groups. So in April 1994, they started an observational campaign with this instrument. And so they used a little bit different approach. Instead of having an absorption cell, they had starlight fed in by optical fiber and a thorium hollow cathode lamp for reference, also fed in by an optical fiber, and then combined into a shell grating. Shell gratings have relatively spare ruling, and but so you can have quite a large area, and in this way have a very good light collection ability, and then finally into a order separator and CCD camera. And here once again you see a absorption spectrum. Of course, this has to be. They had to build this very stable. And but the advantage, there is no moving parts, and they could record very quickly. In 30 minutes, they could record a spectrum, and which means that they could design. I should say also that they had a precision of 13 meters per second, which is clearly enough to observe exoplanets. A shell grating, as I mentioned, thorium lamp as reference, and no moving parts. Exposure time 30 minutes or less to record a stellar spectrum between roughly the visible region of the electromagnetic spectrum from 390 to 680 nanometer. And they used this spectrometer at the Haute-Provence Observatory in South France, and they had also designed the observations so that they could online observe. They could sit online and reduce the data. This is different from the campaigns by Campbell and Walker. They had to record data, go all the way back to UBC Canada, and then reduce the data. So here they had a clear advantage by thinking very carefully and using modern technology. I mean, CCD camera, optical fibers. Both of these inventions have been awarded Nobel Prize. So here you see the Haute-Provence Observatory in South France. It's located about here. And here is the observatory. It's not a very big telescope. I mean, it's just under 2-meter reflector. And they included 142 stars in the campaign. And already in 1994, they observed the Jupiter-like planet orbiting 51 Pegasi, which is a sun-like star. What was very surprising was that it had a very short orbital period, 4.23 days. And of course, this was a matter of concern because the signal you're looking for an exoplanet can also be, there can be false positives. There can be effects of the photosphere that could mimic this motion of a star. So one has to be careful, and I think that Major, of course, with his extensive experience from studying binaries, he was very well aware of this, and he knew how to sort of argue that this was not a photospheric effect, it was really an exoplanet. And here comes now one of these remarkable coincidences that happen sometimes in science. I mean, I mentioned to you earlier that the review article sort of summarizing more than 10 years of research in August 1995 ended with saying that nothing has been observed. And arriving to Nature on August 29, 1995, was the article by Major and Kellogg. And Gordon Walker was selected as one of the referees for this paper. So he was one of the first. They had kept this secret. He was one of the first to realize that that they had observed an exoplanet. So that's really cruel, isn't it? The fact that it was some skepticism, of course. They also announced these results in a conference in early October in Florence, Firenze, and the paper was published in Nature on November 23. And it really had the title, a Jupiter mass companion to a solar-type star. So here they were confident that they had seen an exoplanet. There was no question about it. And because of the very short, very short orbital period, it was quite straightforward for other groups, for example, Marcy and Butler, to just take their instrument, look at 51 Pegasi, and confirm that they could also see this curve. And this is now from the original publication by Major and Kellogg. And what you see here is the radial velocity on this axis and the orbital phase on this one. So you see that it goes up to just over close to 60 meters per second in radial velocity, and then it goes down to minus about 60 and so on. And by measuring then the distance here between here and here, or here and here, you get the orbital period, and by measuring the amplitude, you get the mass with a correcting factor of the inclination angle. But they could conclude that this was basically a Jupiter-type planet. And just to emphasize once again the technique, it's you're looking at the blue shift and the red shift, and this curve is actually from the confirmation by Marcy and Butler. That they recorded, and you can see it's very similar to this one. And so already as a note added in reference, Major and Kellogg could already in the Nature paper confirm that other groups had observed this curve as well. So that, of course, was a strong point. And here you see the what's called the 51 Pegasi b. This is Jupiter-like planet, and here is the star, the mother star. It's clear that Campbell and Walker could have, had they directed their instrument towards 51 Pegasi, they had the accuracy to observe this planet, but they never did it. And I think here the reason was, of course, that they had a much smaller sample of stars. Major and Kellogg, they had designed everything so that they should sample many more stars, and as you can see, they had 142 that they could observe in a rather short time. So this was, I think, the winning strategy in this race. And I should say also another interesting point here from a sociological point of view is that looking for exoplanet was really sort of almost in the backwater of astronomy in the 1980s. This was not a major theme and there was also these problems with false positives, and so it didn't really have a very, very high reputation looking for planets. And I'm not even sure if Major highlighted the search for planets. He could probably argue that we are looking for brown dwarfs, for example. But once the really first exoplanet had been discovered, and everybody realized this is really a correct observation, this field really exploded. And a few years, maybe 5 years after the first observation, also the transit photometry method was developed. So and the physics here is even simpler than for radial velocity method. If you have an observer here, and when the planet is passing through the surface of the star, the intensity will go down a little bit and then go up a little bit when the planet has disappeared here. So that's just a very simple physical origin of the transit method. And it turned out that the transit method is very well suited for satellite missions. The reason being, of course, that if you sit on the Earth, you have a layer of atmosphere, and we all know that if we look at stars, I mean, their intensity will change a little bit. I mean, you probably have in Norway also the Blinka Lilla Stjärna. So it's no surprise, I mean, that a satellite is much better. So the very first satellite mission was a European one, Corot, in 2006 to 2013. You see this satellite, but the one that really collected many observations, more than, I think, maybe 2,000 or so, was the Kepler satellite that was running between 2009 and 2018. And they both relied on the transit method. But once you have observed a planet with the transit method, it's of course also possible to direct a ground-based instrument looking for its radial velocity effect. Presently, there is the TESS mission. It was launched in 2018. This is a NASA project also. The principle is the same as Kepler. It's just that it's covered a much larger part of space, so that it will observe many more planets. And what has been surprising, I mean, what was surprising already from the first observation, if you remember, I told you that the orbital period of this first Jupiter-like planet was 4.23 days. That's an extremely short period. I mean, it's less than a week. And you have a planet of the size of Jupiter. Jupiter orbits around the Sun with 12 years. Our Earth was 1 year. So 4 days was very surprising. But what has been realized by many observations, and what you see on this diagram is here a diagram with planet mass, or minimum mass on this axis, and orbital period on this axis. And of course the Earth mass 1 and 365 days. But the planets of our solar system are a little bit outliers compared with the main part of the observed exoplanet. The number is now more than 4,000, I should say. And they are grouped in 3 categories. These categories here, usually called the hot Jupiters. That's where the first one was discovered, the 51 Pegasi b. These are the warm Jupiters, and these are the super-Earth planets. And this is mainly by the radial velocity method, but there are also some of these that have been observed with the transit method. The good thing, if you can observe both with transit and radial, it means that you get both the radius and the mass, and this means that you get the density of the planet. So that's really, if one can combine, if there are sufficiently good conditions so that you can do both, I mean, that's a real advantage. Here we see the radius as a function of orbital period, and once again the planets in our solar system are a little bit outliers of the main part of planets that have been observed. And so it's clear, for example, with the very first planet that was observed, that it wasn't formed so close to the star. It was formed maybe at a distance comparable to Jupiter's distance to the Sun, and then migrated inwards. So it seems like not at all planetary systems are as stable as our planetary system. And one could just imagine, I mean, what would happen if Jupiter start to migrate towards the Sun? I mean, that would be a major disaster for the Earth. But it seems like it's stable. So this observation has, of course, caused people working with planetary formation to rethink the different mechanisms. Because prior to the first observation of an exoplanet, the only system we had was our solar system. And it's quite natural that you try to design theoretical models that would predict what we observe in our solar system. But now they have to rethink this. And this is a science in itself, of course, the planet formation, evolution of planets. Where can we look for exoplanets? Well, here is the Milky Way, our galaxy. We are about 30,000 light years from the center of the galaxy, where there is a massive black hole, by the way. And we can search for, we have presently the sensitivity to search for exoplanets in this region. It's about a couple of thousand light years from the Earth. And I think what we will see in the future is that one will concentrate on exoplanets that are really nearby our own Earth, because that's where you can do the most detailed studies. But by making the statistics of what we have observed here and extrapolating to the whole Milky Way suggests that there could be maybe 100 billion planetary systems just in our galaxy. And in future we have 3 missions. I just selected 3. There are certainly more than these, but the first one here that will be launched now in December. It's a European satellite mission called CHEOPS, and it will concentrate on planetary systems that have been already observed. So it will not search for new exoplanets, but really focus on such planets that have been observed, and try to do more detailed studies. James Webb Telescope is more ambitious, has been going on for a number of years. It's going to basically replace the Hubble Space Telescope. It's and here you can do really infrared spectroscopy, and this will be important in search for planetary atmospheres. And finally, there is the Extremely Large Telescope, 2025, and exoplanet search will be an important, or studies will be an important part of the science case here. So just to summarize today's research on exoplanets, I mean, how do we explain the origin and development of planetary systems? The diversity came as a surprise. Oops. One will identify and characterize exoplanets in the habitable zone, search for biosignatures. In September 2019, just a couple of months ago, was the first observation of water vapor in an atmosphere of an exoplanet in the habitable zone. The habitable zone is when you have a, shall we say, not too close to the star when it becomes too hot, and not too far from the star when it becomes too cold, but we're really like we are here in a habitable zone on Earth. And finally, I think a new direction will be, once there are more detailed observations of atmospheres, one can start to look at the climate of exoplanets. And then it will be possible to explore parameter spaces that we don't have here on Earth, and learn more about climate, use climate models, and see how well they can describe climates of exoplanets. And so I think it's very clear that exoplanet research is a new branch of astrophysics. It's I noticed, I went to a conference in Santa Barbara in May just to check out how this field developed. I mean, there are many conferences, and I noticed that there were a lot of young people at this conference. There was quite a large fraction of women, actually, playing a very important role in the conference. I was invited speakers, panel discussions, chairpersons, and so on and so forth. So I think it's and I think one reason is that if you enter this field, there are so many different types of planetary systems that you can choose to study. So it's like a big smorgasbord, and you don't have to compete with each other too much. You can pick one and go in for detailed studies of that one. So I think that's an appealing aspect of this new field. So I think that was the last, yeah. So I thank you for the attention. Yeah, you continue directly.
Yeah,
we don't take questions now.
We take questions after I understand.
Okay, yep.
Yeah. There. Well, thank you for a very exciting talk. I was asked to just say a few words about what is being done at the University of Oslo in the fields which we now have heard about, which are awarded the Nobel Prize in 2019. I'm Per Lilja. I'm head of the Institute of Theoretical Astrophysics, which is, in fact, Norway's only astronomy department. Well, astronomy has been a part of the University of Oslo since 1814. In 1834, the Oslo University Observatory was opened, which we see here. In 1934, it was closed, and the Institute of Theoretical Astrophysics building was finished, where astronomy is today in Norway. In the Institute of Theoretical Astrophysics, which is a misnomer, I would say, because we are doing as much as observational and theoretical astronomy, but it's a historical name. I'll now see what we are doing, which is something which has been pioneered by these people. First, start with cosmology. As we heard, Jim Peebles, he's done so much in cosmology, really laid the foundations for a large number of fields here, studying the Big Bang, studying the large-scale structure of the universe, which even he wrote a book called that, which was my Bible as a student. Studied the cosmic microwave background radiation, or rather even predicted it. Nucleosynthesis in the Big Bang, statistical distribution of galaxies, predicted cold dark matter, dark energy, and lots of other stuff. I must say that I myself have been very inspired by Jim Peebles. In a paper from 1977, in a series of 12 papers, statistical analysis of catalogs of extragalactic objects, with student Seldner, he had a cross-correlation of the Abel and 10 Archimedes chain-Wirtan catalogs. Just 10 years later, as part of my PhD thesis, I tried to improve on this, and has almost the same title. It was a great inspiration for myself. At the Institute of Theoretical Astrophysics, we have a section of cosmology and extragalactic astrophysics. The major things we are doing, and I think all of them are really following up stuff which Jim Peebles have done, looking at the theoretical foundations of cosmology, analysis of data from cosmic microwave background experiments in space, with the Planck satellites, in balloons and on grounds. We are studying the large-scale structure of the universe, predicting how it will be with different models of dark energy and modified gravity, participating in the coming Euclid satellite, which I will just briefly return to. We are studying interaction of galaxy formation with the surrounding environment around the galaxy, also something which Jim Peebles has been into. And finally, we are, more observational, observing young galaxies in the early universe. So we are really following up Jim Peebles in a large number of different ways. Here I'll just mention the Planck satellite, where we have had a major role, which we heard about previously, which really mapped out both the temperature and polarization in homogeneities in the universe, giving the most accurate numbers we now have for the cosmological parameters. This is the curvature of the universe, showing that this is extremely close, putting very stringent limit that the universe is flat. The dark matter is very strongly with 0.007 here. The Hubble constant, which gives the expansion rate of the universe. The ratio of pressure and energy density in the universe, which is extremely close to what is predicted by lambda, the cosmological constant. This number should be -1 if we have a cosmological constant, and we see that the -1 is, it is, with quite high accuracy. And this lambda CDM, where which was really predicted by Peebles also, fits very nicely all the data we have now. Of course, there are still problems, there are some tensions, and I won't have time to talk about those. And there isn't really no good theoretical understanding behind lambda either, but that's another thing. What we've done in Oslo with the Planck data, well, it's been quite all over the field, but the most important we've done is how to subtract the different physical foregrounds, because what we see with the Planck satellite is not only radiation coming from the microwave background, but we also have radiation coming from our own galaxy, from dust, from gas in our own galaxy, different types of physical process in this gas, and how to subtract that in the best possible way has been the main part of what has been done in Oslo on the Planck data. We are participating in the future, which is the Euclid satellite, which will be launched in 2022. I think even this was supposed to be, let's see. Yeah, it was supposed to be able to move here. But we just see the size of it here. It's to be launched in June 2022, and we are participating heavily in this, which is also to test lots of the predictions of Jim Peebles. Going over to Exoplanet and Didier Queloz and Michel Mayor. We heard, no, I wrote 1992, I meant 1995, sorry. But today we know, well, they discovered the first one. Today we know more than 4,000 in 3,000 different systems. It's become one of the most important research fields in astronomy today, from nothing in the early 1990s. We have questions: how many planets out there could be habitable? How many have life? Well, we haven't discovered that yet. And is there advanced life out there who might even communicate with us? Extremely important questions for mankind. Some of the questions people have thought about since the beginning of civilization. At the Institute of Theoretical Astrophysics, we are not at the moment really doing anything there, except from we have a bachelor course in observational astronomy, where the students, third-year bachelor students, they discovered, well, it was known from before, but with an amateur telescope using the transit method, they showed that you very easily can find exoplanets, even with a quite small amateur telescope. But the Department of Geosciences has a center of excellence called the Center for Earth Evolution and Dynamics, and they have a group called Earth and Beyond Comparative Planetology, led by Professor Stephanie Werner. And they are now going from studying the planet things in our own solar system to outside, and are into exoplanets also, and they are participating in the European Space Agency's Plato mission, which is a drawing over here, with aim to be launched in 2026, which aim is to discover more, well, a large number of, through the transit method, new exoplanets near the Sun. So it's, while the Kepler, which has discovered most of the exoplanets so far, they looked on a small field on the sky, which meant that you had to look at, to get a large number of stars, you had to look at many stars, at stars quite far away, I mean. Well, what Plato will do is to look all around us with this array of small telescopes and discover exoplanets nearby. And they are, of course, more interesting because then you can study them in more detail. So that was what I had about what is being done in the fields of what the Nobel Prize is given for this year at the University of Oslo. Thank you.
Any questions?
So I have a quick question about these nice scatter plots that showed that the planets in our system are sort of outliers. Do we know to what extent that is like a sampling effect? I mean, I assume it's easier to observe planets with.
Yes, you're quite right. I mean, that could be a sampling effect that is, of course, easier to observe hot and warm Jupiters than small rocky planets. That's clear. So I think we need more samples before we can really say that our solar system is a little bit odd in that respect. But you know, when it comes to exoplanets, if you make a Google exoplanets and look at news, there are news every day. It's really amazing how active it is.
So a bit less scientific question. Is there a reason why the Nobel Prize for the exoplanets was only this year, since it's now, as you said, there's so many, and the first one was discovered over 10 years ago?
I mean, it takes time to really develop a Nobel Prize. So it's and also to understand how important the field becomes. And I think that I mean, I cannot really speculate how we develop this, but it's certainly so that once we now came to the decision, we felt that these two persons were really the one to award. And it's of course a little bit, I mean, it's a little bit special here that you have one discovery which leads to the formation of an entirely new field of astrophysics, and so that's, and then, but I cannot really explain how the, because as you know, this is a secret process that will, if you, well, you can, in 50 years you can come to Stockholm and say that you're a historian of science and you want to study the Nobel Prize for exoplanets.
Do we have any more questions? Okay, if not, I would like to thank you very much for coming once again. Hope to see you or one of your colleagues next year.
Yeah.
And
okay.
safe travels back
Thank you.
to Stockholm.
Thank you.
Thank you all for coming.